In this lesson we're going to look at intersecting planes, and then we're going to look at more complex questions that involve intersecting planes when we mightn't be given some information and we have to find it using auxiliary views. So to start off, we look at this sample question. So in this sample question we have two lamina, a yellow and a green lamina. So a lamina is a triangular piece in space of what actually could be an oblique plane. So if we were to extend this green triangle onto the ground and onto the back wall, we'd have our oblique plane. Now in this question what we're going to look at is, these are the coordinates given. So we have coordinates given here. So we have the A point. So A is for the X coordinate then is 140. So what we're doing here is X is the horizontal distance, Y is the vertical distance, and Z then is the distance from the XY line out the way. So looking at this being represented here, this is for point A here. So we've measured across here for X, then the Y is how far up we measure, and then Z is from the XY line, how far out it is from the XY line. So when we're placing this on a sheet of paper, what we do is we measure out for X, up for Y, and down for Z. Now, so looking at it here, this is setting up the sheet. So we start off with a datum line at the side here. This datum line or reference line here can be used for where we're doing all our measuring from. So when we're measuring for all the X coordinates here, we have to all measure from all the same point. So this could be the side of your page as well. So we're measuring out for A, then it's over 140, up 100, and then down 20, and so on for all the other points. So B then is 120, up 10, and down 80, and so on for C. And basically this is all the points located then. So we've got two triangles in this case. We have ABC and DEF. So then we draw in our two triangles, and we draw them in lightly at the beginning of the drawing because we don't know in this drawing which one is blocked out by the other one. So in this question we need to find the line of intersection between the two triangles. So there's two methods to do this. First we'll start off with the horizontal slicing method. Now the horizontal slicing method is my preferred option. So what it is, it's where we take one of the points, so in this case we take point C, and we run a horizontal plane across, slicing through the two laminas. Now when it slices through the two laminas, it cuts into this point here on the line of intersection. So in elevation, all we'll see for this slicing plane is just a level line. Then in plan we're going to see two lines that cross over each other, and where they cross over each other is on the line of intersection. So looking at this here, we draw our level line, we mark off points. So in this case here we have points. We have C2 is one line, and then 1, 3 is another line, and the reason it's 1, 3 is it's on the triangle DEF. So point 1 is on DEF and point 3, so that's the line 1, 3, and then the other line on the triangle ABC is from C to point 2. So when we have them in elevation, we draw them down into plan. So that's our C2 line drawn. Next we bring down point 1, point 2, and where they cross over, that is our point on our line of intersection. Now what we do need to do in this question is we need to find a second point on the line of intersection. So we take another slice across. So in this case here we're taking a slice across from E. So when we take a slice across from E, what we will realize in this question here is we're going to get two lines in plan again, so same as before. So we mark off our points. So our points this time is E4 and 5, 6 are the two lines this time. So we bring down E4 and 5, 6, and what we do in this case here, we have our two lines drawn here. Now, what happens in this occasion here is the two lines don't intersect each other. Now, this sometimes happens, and the reason it happens is if we go back up to our 3D graphic here, what we'll notice is the line of intersection in the graphic here stops here. So what it is, our plane didn't cut through our line of intersection. But what we have to remember is if we were to extend and make this yellow triangle a lot bigger, it would cut through this blue slicing plane here. So what we have to do here is if we extend, so what we can do here is in the plan view here, extend our two lines. So when we extend our two lines, we find a point that would be on the line of intersection. So this point here would be on the line of intersection. So what we do next is we join the 2 points together. And now this is important that some students make a mistake with. When we're drawing the line of intersection can only be where the two triangles overlap. So we found a point down here, but this is not the line of intersection. This helps us find the line of intersection, but the line of intersection can only be where the two triangles overlap. So next we bring up these points, and this here is our line of intersection found. Now in this slideshow here I've also included the auxiliary method. I'm not going to go through it, I'm just going to skip through it. Basically what we're doing here is to do the auxiliary method, we see one of the triangles as a line and then we draw the other triangle in, but we are drawing an extra auxiliary. So just quickly flick through here, you can slow it down and look at it in your own time. Now once we have the line of intersection found, we now can find the dihedral angle. So to find the dihedral angle, always look at 90 degrees to the line of intersection to see it as a true length. So this line of intersection in plan, if we look 90 degrees to it, so set up an x1, y1 line 90 degrees to it and then mark off our point. So we start off, and the best way of doing this is take each triangle separately. So we have ABC, then we take DEF, mark it off, and next we bring up our line of intersection. So we have our true length of our line of intersection now. Now if we look, this is a true length now, and any true length, if we look along a true length, we'll see it as a point. So when we're seeing this true length as a point, we'll see the two triangles as a line, and that allows us to see our dihedral angle. So again, looking along the line of intersection, set up x2, y2. Now we're using a datum line in this case, and the reason for the datum line is just to cut out all this space here, because all of this, remember to find measurements for x2, y2 auxiliary, we go to the previous xy line and measure back the way, but we're measuring a lot of empty space here. So if we use a datum line here, we can measure from the datum line and get the same end result. The only difference on our page is our answer is going to be next to our x2, y2 line rather than down low on the page. So now we take our measurements and mark off our measurements. Now if this is done correctly, ABC should be represented as a line, and then DEF should be represented as a line. Now the only time this doesn't happen is if we're not accurate when we're bringing measurements around. So what we've now found is our dihedral angle, so marked there. So that's a quick overview of finding the line of intersection and then finding the dihedral angle. Now next we'll have a look at a Leaving Cert higher level question from 2012. So this here in the graphic here we can see what we're looking at. So what we're looking at here is a sculpture. So what the sculpture is made up of is two laminar surfaces, and in this question the main issue with this question is we were not given the height for point C or for point E, but we were given their locations on the XY line and in the plan. So if we set it up here first of all, so all the points are marked off here. So in plan we could draw the entire plan, And then the elevation, then we could draw only a certain amount of detail because we didn't have point C, a height for point C or a height for point E. So in this question, what you'll notice here is I've drawn in the 3D graphic here a slicing plane cutting across. So this slicing plane cutting across here, this line here cuts across here, and it happens to be parallel to the edge AD. So that means this is parallel to AD because they're both on the same surface. So imagine if we grab this cutting plane here and slide it all the way down, we'd have a parallel lines all the way down, and it would be parallel to AD. So what that allows us to do then is, if we draw a line in plan then, so what we'll notice here is in the 3D graphic they're showing how we get point P here. So what we can do this is we can take this into our plan view here. So what we have here is a line which is parallel in one view, it will be parallel in all views. So what we have here, line brought across here from C brought across here, that gives us a point here. So this is point P. So now what we can do is point P can be brought up. Now if point P, if we've drawn a parallel line from AD here and AD here, that means we can draw another parallel line in this view, thus giving us point C. So this is point C and point E is the same height. So we can complete the drawing, complete the elevation. Now when we have that much of the question done, the next couple of steps are quite easy. What we have to do first of all is find our dihedral angle. There is no finding a line of intersection this time because AB is the line of intersection between the two surfaces. So what we do here is 90 degrees to the line of intersection. So we're going to mark off the line of intersection and then bring up our points. So now we have a true length of this line of intersection. So anytime we have a true length of the line of intersection, if we look along it, what it allows us to do then is to mark off all these points and find our dihedral angle. So we've all the points marked off, and our two surfaces should represent two lines here because we're looking along the true length of AB, seeing it as a point. So that means then we're seeing this surface as a line, this surface, and we've found the dihedral angle. So the last part that was asked in this question was to find the traces of an oblique plane for the surface AFEB. So this lamina surface here. So we need to find the traces for the oblique plane that contains this lamina here. So if we look at the 3D graphic and we just take one surface on its own and we represent what this lamina surface would look like and what the oblique plane would look like and the traces. Now what you notice is, because AF is on the ground, that is a piece of our horizontal trace. So that means if we extend AF, we can find our horizontal trace. Then what you notice here is on the back wall here we have the vertical trace. So we'll see how we find that vertical trace. So in plan here we're able to draw our horizontal trace very easily. Then to find the vertical trace, if we take another point on the oblique plane, say point B, bring it parallel to HT, then bring this point up and then bring B across. Now that's our vertical trace complete. So that's our vertical trace drawn and our answer and our question fully answered. So that was all that was involved in the 2012 higher level question on intersecting planes. This is the 2016 higher level question on intersecting planes. So what we have in this question here is we have the front of a McDonald's, and what we have is the front section of the McDonald's is made up of these triangular lamina pieces of glass. So the graphic down here shows a representation of it and we're given the coordinates. Now if we look at this question very quickly, we'll notice that in F here we are not given the height of point F, so there will be a challenge to find that height and how we go about finding that height. But to start off with the question, we set up as much as we can. So in this question we can draw the elevation and plan of A, B, C, D, E. Okay, so we have a look at what's asked in the question. So draw the plan of the 4 triangular planes and complete the elevation of ABC, ABD and DEB. And so what they're telling us to do is draw the entire plan, which we can because we have measurements for the entire plan, and then what we go from there then is draw the elevation of 3 of the planes. We can't draw in this 4th plane because we don't have this point here in F. Next part of the question is determine the dihedral angle between plane ABC and ABD. So this triangle here and this triangle here. So what we have is we have the line of intersection. So all we have to do in this case here is look 90 degrees to this line of intersection. So we're going to look up here at an angle, draw our x1, y1 line, find the true length of this line of intersection, and then look down along it and find our dihedral diagonal. Now the next part of the question is draw the elevation and plan of a horizontal line on the surface DEB and determine the true inclination of the surface DEB to the horizontal plane. So what they're asking us to do here is, and basically this sounds like a really difficult question, but it's not. It's actually telling us how to do the question. So what they're telling us to do is to draw the elevation and plan of a horizontal line on DEB and determine the true inclination of this surface to the horizontal plane. So what they're telling us to do is draw a horizontal line. So if we draw a horizontal line across here from E, that's our horizontal line. Now we bring this line down onto the plan view. So from E then draw a horizontal line. What this is basically doing is, if we look along this line, then we'll see this line as a point because it's a true length. If a line is horizontal in elevation, it's going to be a true length in plan. If we look along that true length and it's on this surface, we're going to see this surface as an edge view, and that edge view will give us what angle this plane is to the ground. So that's all they're asking in this question. It's actually telling us how to do it in the actual question here. Now the third part here, the dihedral angle between the surfaces DEB and DEF is 170 degrees. Complete the projections of the surface DEF. So to do this, what we have is we have the line of intersection. So we have the line of intersection here and we have the line of intersection here. So our best thing to do in this case here is just ignore the fact that we don't have the height for F. So what it is, imagine if we did have the height for F, how would we find the dihedral angle? So what we'd do is we'd look 90 degrees to the line of intersection, see it as a point view or as a true length, and then see it as a point view in our next auxiliary. So that's what we do in this question. We look 90 degrees to this line here, see it as a true length, then look up here in our second auxiliary, and then in our second auxiliary what we can do is, instead of find the dihedral angle, we can draw the angle of 170 degrees. Then this allows us to find where point F is, because we will have measurements to find where F is on the drawing. Remember, in the second auxiliary we're going to go back to our previous XY line and get a measurement for F. Okay, so it's quite easy. It's just working backwards when we're given the dihedral angle. But you take it as if you start off the question as if you have all the points and just do a normal dihedral angle. And what you'll realize then towards the end of it, then you draw in your angle of 170 and you'll be able to find F. This is the 2018 higher level question on intersecting planes. So what we have here is a sculpture that's located along the 11 motorway in County Wexford. So they've taken a piece of this structure and represented it on this drawing here. So what we have here is we have points A, B, C, D, E and G. Okay, so what we notice here is point F here is not given to us in this question. So we have to see, obviously we'll have to find that point F to complete this drawing. Now, so if we look at what's asked in the drawing to start off with, first part here is to draw the elevation and plan of the intersecting planes ABC and ABDE. Okay, so we have this surface here and this triangular section in here. Okay, so that's what we're asked to draw so far. Now, after we've that drawn, we determine the dihedral angle between the two planes, so ABC and ABDE. Okay, so that's fairly straightforward. We're given the line of intersection, so we just look at 90 degrees to the line of intersection and then get a true length of it and then look along it like all the previous questions. Now, second part of this, or third part of this question is draw the elevation and plan of point G and determine the distance between point G and point D. So what we have to do there is we have to draw a line from G to B, and there's several ways to figure out what the true distance, and when they're asking for determine the distance between them, they're looking for the true distance between them. So my suggestion, probably the easiest suggestion to do here is imagine G is the top of a cone and B is the base of a cone. So we draw this line down along here in elevation. We do the same in plan. What we know is if B is on the base of the cone and G is the top, what we can do is start drawing the plan of the cone. So if we extend on the plan of the cone till we get horizontal across from G, what we're drawing then is we can bring up this point and find point B up here, and that'll give us what the side of the cone looks like, and that side of the cone will be a true length for the distance between G and B. Now the second part of section C here is the opposite edges AE and GF are on the surface of AEFG are parallel. So complete the elevation and the plan of the surfaces. So what they're telling us in this question here is this line here and this line here are parallel. So we already have this drawn in here. So what we'll notice is to draw in this line, and this is testing your knowledge that you actually understand that if lines are parallel, they're parallel in every view. So what they're asking to do here is from E, if we bring up a line up vertical, in from G, a parallel line to AE brought down here, that finds point F. And then again in plan, what we'll notice here is E is brought up vertically, and then to find where F here is, again a line from G parallel to AE that completes the surface here. So it's actually a fairly easy section to do. Now the final part here is determine the projections of a horizontal line drawn from C which touches the plane AEFG at a point that's 55 away from C. Hence determine indicating degrees the true angle between the horizontal line and the vertical plane. Okay, so if we look at that, what we have to do is in elevation they say it's a horizontal line. So from E it's a horizontal line that is going from C touching this plane somewhere. So it's touching this plane somewhere. So what it is, imagine if we go back to a slicing plane again and we drew a line across here, a slicing plane across here. What it is, it would create a line from across onto this surface here. So we're drawing a line across onto this surface here. Now what we're told in the question is we can bring that line that's on this surface down to plan here. So we can draw that line down onto plan. Then in plan we know it's 55 from C. So what that allows us to do is it allows us to construct an arc from C scribing onto this line here, which we'll have to find, and then we'll be able to complete. So if we look at the solution to this, and we'll see how it's actually, how that is actually done. So what we're looking at here is this is our line from C brought horizontal across. So what it is, it's given us this point F here, and F happens to be the same height as C in this case. So what we have is, we have the line drawn up here, we have this line drawn here, and then from C, scribe our arc 55. So that's given us our horizontal line now. So we can find H here, so that's the line now drawn in our elevation, and then all they're asking then is for the true angle for this horizontal line and the vertical plane. And remember, the vertical plane is this XY line here. Imagine if it's the back wall rising straight up from XY line here. So what it is, a lot of the time in DCG questions, the way they phrase it sounds complicated, but it's actually quite an easy question they're asking. They want to know, this horizontal line, what angle is it making with this back wall, the vertical plane? So you just extend this and measure it here. So in this case here, it's 53 degrees. So this is what your answer should look like on your paper. So we have the cone section here, brought out along here, and our true length put in along here. So it's a relatively straightforward question. In this part of the lesson, we're going to look at skew lines. So skew lines is when two lines are given to you and you have to construct another line connecting the two of them together. And basically what you're asked in this topic is either the shortest distance between the two lines, which will be a perpendicular distance, or the shortest horizontal distance between the two. So where you might see this asked in the question is, you could be told that line A to B is a pipe, and then another pipe is running from C to D, and you want to connect the two of them together by running another pipe between them. And what it is, you might have the restriction that that pipe running between them might have to be horizontal. So what we want to determine in this is, what's the shortest length of pipe that we need to do to connect it. So basically that's what's asked in this question on skew lines. So just to start off here, we have a 3D graphic here showing the two skew lines represented in 3D floating in air. So we have AB and we have CD, and we have the elevation on the vertical plane and the plan on the horizontal plane. Now in this question here, what we have to do is we have to create a plane on one of the lines. So we have to create this laminar surface, and now to create this laminar surface we need to have one of the new edges parallel to our other line, so parallel to CD in this case. So this edge here is going to be parallel to CD. And once we understand that that's what we have to do, the rest of the topic is fairly straightforward to go through. So basically what we're doing here is, we have this line here drawn in our elevation, we have a horizontal line as well put in. Now there's another reason why we use the horizontal line, because if we have a horizontal line in elevation, it's going to be a true length in plan. So it's going to be a true length in plan. So that means when we look along this true length in plan on our auxiliary plane, what we'll end up getting an answer of is our two lines parallel to one another. So our two lines parallel to one another, and we'll be able to construct this line between them. So basically that's what we have to do in this question. So if we look at an exam type question here, so we're given our two lines. The first thing we have to do is we have to choose one of the lines in which we draw our horizontal line from. So what we notice here is this point here, the lines do not intersect on this point here, right? And the reason they don't intersect is, if they did intersect, this intersection would be in the same place in plan, which clearly it isn't. It's well away from it. So they don't, it looks like they're intersecting one another, but they're not, because that intersecting point should be in the same place in both views. Now, so in this question we'll take a horizontal line from A. Now in this question it doesn't make any difference which line, but in this case we'll take it from A. So if we're taking a horizontal line from A, from B we're going to construct a line that is parallel to CD. That gives us a point P. Now we bring point P down to plan, and what we're going to do is this line from B here, again parallel lines in this view are going to be parallel in this view. So this blue line is parallel to CD. So we can bring down point P now, and now we have our horizontal line in elevation brought down to plan. So we know this is a true length in plan. So if we look along this true length and construct our auxiliary, so we're looking along P, we're marking off our heights from our previous XY line. So we're finding all our heights. So we have AB found, and then do the same for CD. And if we have this done correctly, the two lines have to appear parallel to one another. They have to appear parallel to one another. And that's the whole reason for taking this blue line parallel to CD and the blue line here parallel to CD. It's to get these two lines to appear parallel to one another. Now from this stage here we have to find the shortest perpendicular distance. So to find the shortest perpendicular distance, we look in 90 degrees to the two parallel lines. So 90 degrees to two parallel lines, set up an x2, y2 line, and then project our lines up, getting our measurements from our previous xy line backed away. So we mark off A and B, and then we do the same for C and D. And then what we've now found is the location on which the lines, we can construct a point between them. So this point now is brought down to our first auxiliary. So this here is our shortest perpendicular distance now found. We bring it down to plan, and then we construct it up into the elevation. So that's our shortest perpendicular distance, sometimes asked as the shortest distance between the two lines. So that's our shortest distance. Now in this question here, similar question again, but we're looking for the shortest horizontal distance. So what this means is the line connecting A, B and CD together has to be a horizontal line. So if it's a horizontal line in elevation, the line needs to be horizontal in our finished drawing. So to start it off, we construct it the same way as the previous one. This time we're going to take a level line from C, and this time we're going to go from D parallel to AB. So that's our point P found. Bring P down. So from D in plan, parallel to AB again, P brought down, and then we construct this green line. Now this green line, because it's horizontal in elevation, it's a true length in plan. So that means if we look along that true length now, construct our x1, y1 line, find our two lines now, again getting our measurements from our previous xy line, we should have two parallel lines. So we have two parallel lines here. Now in this question we're looking for the shortest horizontal distance. So what that means is in this first auxiliary the line needs to be horizontal, because remember when we're bringing this line back to our elevation it needs to be horizontal. So this line needs to be horizontal in this view and this view. So to find the shortest horizontal distance, we need to construct an xy line which is looking 90 degrees to x1, y1. So we construct x2, y2 90 degrees to x1, y1. So then it's a matter of just constructing our two lines again. So we've AB and CD constructed, and where they cross over now, when we bring back this point, that'll be our horizontal line. So we mark it off in plan, then bring it up, and it has to be horizontal in our elevation. So the only difference in this one is instead of looking 90 degrees to the two lines, we're looking 90 degrees to x1, y1. Now the third option is if we want to find the shortest distance at an angle. So for example, in this question, what we might be told is we want the shortest horizontal distance between the two lines, but it needs to be at 45 degrees. So we need to construct a line that is at 45 degrees from CD to AB, and it needs to be at 45 degrees. So we'll look at how we set this up. So to start this off, we construct a line from B, in this case, horizontal line. So from A, we need to draw a line parallel to CD. That finds us point P. Now we do the same in plan. So from A, construct a line parallel to CD. Bring point P down and then draw our green line, which is our horizontal line. So in plan it's a true length. Now we're going to look along this true length. So to construct our first auxiliary, so our first auxiliary should show our two lines parallel to one another. Now if it's not drawn parallel to one another, we've constructed something incorrectly. So we have to retrace our steps and see what we've done wrong. So we've two parallel lines here. Now in this question, we're going to be told it's 45 degrees. So the angle we're going to use in this case here is 45 degrees. So the shortest horizontal distance, 45 degrees. So in the previous two questions, we looked 90 degrees to the two lines or 90 degrees to x1, y1. So in this case, we're going to look at 45 degrees. So we're going to project at 45 degrees to x1, y1. So what we're doing is setting up x2, y2, and then construct our two lines, same as what we did in previous questions. So we have our two lines constructed, and then we have our point found. We bring this back, and this line now is at 45 degrees. So we bring this point back now to the two previous views, and that's our line at 45 degrees. Now it will not appear at 45 degrees in elevation because we're not looking in 90 degrees to it. So what it is, imagine this was top of a cone here and this was the base of the cone, and we rotated this around and drew a cone in plan and drew the sides of our cone would be at 45 degrees. That's how we'd prove that that line was at 45 degrees. But we don't need to do this in this case. Now in this case here, we'll set up the three different drawings. So what we have here is this is the shortest perpendicular distance. So to construct the shortest perpendicular distance, we go 90 degrees to the two lines. So if I quickly go through here and show you the difference between them. So the first one is the shortest perpendicular distance. So we're going 90 degrees to the two lines. The next one, the shortest horizontal distance. So we go 90 degrees to x2, y2. So that's our shortest horizontal distance. So we have two different answers. And then in the third one, we go with at an angle of 45 degrees. So we project 45 degrees to x2, y2. And then bring this back. So what we have here is, this is three answers. So we have all three possible questions put on one sheet here to show how this can be done. So shortest perpendicular distance 90 degrees to our two lines, shortest horizontal 90 degrees to x2, y2, and then if it's at a given angle, whatever the angle is, say in this case 45 degrees to x2, y2. Now we're going to look at some short questions that are asked on the Leave Insert paper based on skew lines. So what we have in this case here is determine the projections of the shortest distance between the two lines. So what we have here is these are two flight paths. So what we have here is AB is one flight path for an airplane and CD is another flight path. So what we want to do is determine the shortest distance between the two aircraft. So what's the closest they'll ever be to one another? Okay, so this is a useful method of using skew lines in real life. So to construct this, what we start off with is take one of our lines, so from A in this case, A parallel or horizontal, then from B parallel to CD, we locate point P, bring this down to plan by extending B parallel to CD. That finds us our horizontal line in plan, which we now know is a true length. So we look along this true length. So we're going to look along this true length, x2, y2. Find our two lines then, AB and CD. And what we have is we have our two lines here. And now because it's the shortest distance between them, we're going to project perpendicular to the two lines. So perpendicular to the two lines here. So what we have here is AB and CD. They're crossing over here. So what we have here is, this is the distance now between the two. So what we have now is constructed the distance between the two. So this here is the closest, in this case here, that the two airplanes get together. Now the only place you can show this distance is in this auxiliary here. So this auxiliary here is showing the true distance between the two airplanes. You can't show it in any of the other two views here because it's not a true distance. This is your true length in this view here in the auxiliary. Now this is another question based on skew lines. So again, it's a short question. So the graphic below shows a number of sloping arms in a sculpture. Two arms are represented by skew lines. Determine the projections of the shortest horizontal distance between the two. So for example, in this sculpture, if we wanted to connect another bar between the two skew lines and connect them together, where would the best location for that horizontal bar be, and the shortest distance it could be? So if we look at this question here, again, from A, take a horizontal line, from B, parallel to the other line. Then, in plan, from B, parallel to CD, and then that's how we locate point P, and this is our true length. Look along this true length then, to construct our first auxiliary. So our first auxiliary will give us the line AB, and CD as two parallel lines. So we have our two lines set up. Now, remember, it's shortest horizontal distance, so we need to go 90 degrees to x1, y1. So we construct our second auxiliary. So we construct AB and CD, join them together, and then bring this point back together. This is our shortest horizontal distance now. We draw this in our plan view and then in our elevation. Now in this question, this sample question here, we'll construct skew lines again. So what we're going to do in this question is we extend out from A, B is parallel to P, then bring down point P, then again look along our true length, set up our first auxiliary, find AB and CD. Then we're looking for the shortest horizontal distance again in this question. So in this question, you're going 90 degrees to x1, y1, and then project up our second auxiliary by getting our measurements from our previous xy line back the way. So we have AB found, we join in AB and CD. We have our point found. We're able to bring this back to our first auxiliary to locate the horizontal distance. Now we can draw this back to our plan and then construct an elevation. And this is all that is involved in skew lines. So this is the topic of skew lines. Normally comes up as a short question in Leaving Cert DCG.